So far we have talked about modules and linear maps between them. We called those maps homomorphisms. But we also know natural examples of maps that are not linear but bilinear. So if we have a vector space Rn, then we know that we can define scalar product from Rn cross Rn to R, where we send a pair of vectors to their dot product or scalar product. Let me call this map P for product. So P denotes this map that takes V and W and sends it to V dot W. P is not a module homomorphism. It is not R-linear because P of V plus V prime and W plus W prime is not equal to P of V comma W plus P of V prime comma W prime. In general, it is not equal to because we also get cross terms. So we have P of V W, and we also have the term, the product of the dot product of V prime with W and the dot product of V with W prime, and then P of V prime and W prime. And so now we give a definition given two modules M and N and a target module T. So we have three R modules where R is a commutative ring. We say that a function B from M cross N to P to T is R bilinear, or if we know that the base ring is R, we can call it just bilinear. If for every M in M and every element N in N, functions where we fix the corresponding argument are linear. So functions B and Bm, and this is the free entry, and B dash comma N are linear. That is, they are module homomorphisms. Explicitly, this means that for every pair of elements M and M prime in M capital, and for every pair of elements N and N prime in N capital, and also for every scalar R, we have that B is multiplicative in each argument, so P of R M comma N is equal to r times b of m comma n, and this is also equal to b applied to m comma r n. So if we multiply one of the entries by a scalar, we can move the scalar out. And b should also be additive in both entries. So b of m plus m prime comma n is equal to b of m comma n plus b of m prime comma n. So this is additivity in the first entry, and likewise for the second entry, we get b of m comma n prime m comma n plus b of m comma n prime. And I also define the set of all bilinear functions from m cross n to t by this notation: bil sub r, m comma n, and t here. So this is the set of all bilinear maps from m cross n to t. And I want to note that here I write this cross. We earlier defined the direct product of modules, but here we don't remember the structure of a module. So here we view it as a set. We view this gadget m cross n as a set. And this is because b is not a homomorphism from m cross n to t. It is a bilinear function, or a bilinear map. And now it is time to consider a lot of examples. So the 0th example, the zero map from m cross n to t is always bilinear. So by now you should have already become experts in zero examples, and you should see that that zero is trivially bilinear. Then I already mentioned that scalar product is an example. In fact, we modeled bilinear maps after this example. Then, if R is any ring, any commutative associative ring with a unit, then the multiplication map R cross R to R is R bilinear. And we can check it by looking at the axioms. So if we multiply two elements, let's say x and y, and we take a scalar r, and we want to multiply Rx by y. So we get that it is Rx, y, and we know that we assume that all our rings are associative, so I'm not writing any brackets here. So if I mark xy as the first multiplication, then I can view xy as the result of applying mult to x comma y. So it is equal to r times mult x comma y. But we also assume that the ring R is commutative. So we have that Rxy is equal to x dot ry. And this is the result of applying mult to x comma ry. And so we got our first axiom. And axiom number 2 and axiom number 3, they follow from distributivity laws. Distributivity of multiplication in a ring. So I will just check number 2 because number 3 is exactly the same. So multiplying x plus x prime by y, we can write it simply as x plus x prime y. And by distributivity it is xy plus x prime y. So we again can write it as mult x comma y plus mult x prime comma y, and we get exactly the second axiom. And so we checked this as well. And so multiplication in the ring is bilinear. Example number 3. If R is a ring and M is an R module, then the structure map that multiplies an element of M by a scalar in R, I will denote this structure map by S. Then this map is also bilinear. And the checks here are the same as in the second example. The fourth example is more like a general construction. If B is a bilinear map from M cross N to T, and phi from T to Q is linear, so if phi is a homomorphism, then the composition of phi with B is a bilinear map. And I'm going to leave this as a homework exercise. For the next example, I'm going to give a definition for an R module M. We can define the dual module M star we define it as the module of homomorphisms from M to R. And using this notion, we can give our fifth example. So if phi is a homomorphism from M to the base ring R, and psi is a homomorphism from N to the base ring R, then we can define the product phi psi from M cross N into R, and it will be bilinear. Phi psi applied to M comma N is defined as the product of phi applied to M and psi applied to N, and this is bilinear. So basically, example number 5 tells us that a product of two linear things is bilinear. So we considered a lot of examples, and we saw that one of the structure maps of a module is bilinear, but for example, addition is not bilinear, it is linear. So if I consider a module M and I take addition, so this map, I will call it add, is linear but not bilinear in general, because if we consider add of M plus M prime, comma N plus N prime, so we add all of those together, and it will be the same as adding the sum of M and N to the sum of M prime and N prime. So we don't get those cross terms. So adding M plus M prime to N is not equal to adding M to N and then adding the sum of M prime and N, because then N would appear twice in this sum. And modifying the fifth example of bilinear maps, if we have a homomorphism from M to R and a homomorphism from M to R, then their sum, phi plus psi from M cross N to R, is linear but not bilinear. And the sum is defined as you expect it to be. So phi plus psi applied to m comma n is equal to the sum of phi of m and psi of n. And here is an interesting example of a map. Let us consider the complex norm n from C cross C to C, which takes a pair of elements Z and W and maps them to Z times W conjugate. And I call it a complex norm because n of Z comma Z is equal to Z times Z conjugate, which is the square of the length of this vector. So this map N is not C-linear. And this is because we can take complex numbers Z and W and let us try to multiply W by I. So apply N to Z comma I W. This is equal to Z times IW conjugate. Conjugation is multiplicative, so we get Z times I conjugate times W conjugate. And the conjugate of I is minus I because we reflect with respect to the real axis. So we get minus I times Z times W bar. So we get that N applied to Z, comma IW is equal to minus I N applied to Z, comma W. So we couldn't pull I out without changing its sign. And so N is not C-linear. But N is R-linear. And this is because for the same reason as we showed here, if we take some real number instead of I, it would not change after complex conjugation. So if lambda is a real number, then N applied to Z comma lambda W is equal to Z applied to lambda W complex conjugate. And so we pull lambda out. So lambda bar here times Z W bar. And lambda bar is equal to lambda because its imaginary part is equal to 0, because lambda is a real number. So it is equal to lambda applied to N of Z comma W. But also if we view this as one number, as one complex number, lambda Z, we can write it as N of lambda Z comma W. And it is easy to see that N is additive. For example, let me take W plus W prime. So we have Z times W plus W prime complex conjugate. So changing the sign of the imaginary part is additive, so we have Z times W bar plus W prime bar. So you can see that this is ZW bar plus ZW prime bar, which is n of z comma w plus n of z comma w prime. And even easier than that is checking that n of z plus z prime comma w is equal to n of z comma w plus n of z prime comma w. And so we check that n is R bilinear. Bilinear. And here also bilinear. And so this example shows us that being bilinear can be a notion that depends on the base ring of your choice. So we saw a lot of examples of bilinear maps, and now I want to prove that the set of all bilinear maps forms a module. So bilinear maps from M, M to a test module T. I just want to recall our notation that this is the set of all bilinear maps. From M cross M to T. And the claim that I'm making is that if M and T are R modules, then this set is an R module too. And the structure of the R module that we give it is the following. So if we have two bilinear maps, B and C, from M cross M to T, then I define their sum on M comma N as the sum of B on M comma N and C on M comma N. And the scalar multiplication, if I have a scalar R in the base ring R, then I define RB as the map that takes M comma N to R times B of M comma N. And let me prove this fact. So the first thing to check is that the results of both operations are still bilinear forms. So we want to check that B plus C and RB are bilinear maps. From M cross M to T. And let me start with B plus C. So first, additivity in the first entry, M plus M prime comma N. Using the definition of B plus C, we write it as B of M plus M prime comma N plus C of M plus M prime comma N. And now because B and C are both bilinear, we can split this part into B of M comma N plus B of M prime comma N. And similar with C, we write it as C of M comma N plus C of M prime comma N, because we use the fact that if we fix N here, then C is linear in the first part. And now we rearrange the summand. So we take this summand B of M comma N and C of M comma N, and by definition this is equal to, by this definition it is equal to B plus C applied to M comma N. And now the other two summands. It is B plus C applied to M prime comma N, these two summands. And so we prove that B plus C is additive in the first entry if the second is fixed. And a similar check would prove the axiom for the second entry. So I will omit it because it is exactly the same, except for writing n as n plus n prime and fixing m. And now let's see how B plus C behaves with respect to multiplying the first entry by a scalar. So B plus C applied to R m comma n is equal to B of R m comma n plus C of R m comma n, which is R times B of mn plus R times C of mn. And so we can use distributivity and pull R out of the parentheses. So we would get R times B of mn plus C of mn, which is the definition of B plus C applied to m comma n. And so we can pull a scalar out of the brackets here. And similarly for n, if we replace n with Rn, we can pull the scalar out. So B plus C is R bilinear. And now I want to check that RB is a bilinear form. So RB applied to m plus m prime comma n, it is equal to R times B of m plus m prime comma n. By bilinearity of B, we get that this is equal to B of mn plus B of m prime comma n. And so I use distributivity again to write it immediately as R times B of mn plus R times B of m prime n. And using the definition of multiplying a bilinear form by a scalar, I get additivity in the first entry. Finally, RB times Sm comma n, it is R times B of Sm comma n, and because B is bilinear, we get Rs times B of m comma n. And exchanging R and S, using that R is commutative, we get that this is equal to S times RB applied to M comma N. And so we proved that RB is also a bilinear map. To see that this set is an R module, we need to check that it is an abelian group with respect to addition, but we know that there is a neutral element with respect to addition, so we know that 0 is a bilinear form. And the definition of adding two bilinear forms is commutative, because we can easily exchange these two summands, because the target module T is an abelian group with respect to addition. And if we take a bilinear form, then -1 times B is also a bilinear map. And it is such that -1B plus B is equal to 0. So every element admits an additive inverse. Then associativity, which checks somewhat similar as this part. If we have a bilinear form B, then Rs times B as a bilinear form is equal to R times SB. And the final check is that if we have two scalars, R plus S, applied to B, this should be equal as a bilinear form to RB plus SB. And distributivity in the other direction is that if we have two bilinear forms B and C, then R times BC is equal to RB plus RC. So these last two checks are very similar to what we did here. We need to plug in elements m comma n into both of these, into the left hand side and into the right hand side, and check that what we get on both sides is the same element of T. And if you do that, it will conclude the proof.